our intuitive picture here for what the damping should look like outside the potential barrier should match up with something we can do explicitly, which is just to show that this form of the wave function is a good solution out there in this region where x is, the absolute value of x is very large, so either on the negative side of the barrier or the positive side of the barrier. So remember what the Schrödinger equation looks like. It's minus h bar squared over 2m, the second derivative of psi with respect to x, plus the potential, in this case 1/2 kx squared times psi is equal to E times psi. So for very, very large x, this is what we're talking about way out here, if energy is a constant, then this piece right here is going to be much, much larger. So when I take something like a simple rearrangement, and do that all times, I guess, 2m over h bar squared. The second term, E, is going to be quite small compared to the 1/2 kx squared. So I have that. The first derivative of psi is easy enough to do. I'm just going to do this by chain rule. I have e to the minus u, so I have to do the derivative of that, and then I have to do du dx. So the first derivative will look like this. The second derivative will have two terms associated with it. Because I'll have to do a chain rule. I'll have to first take the derivative of this times that, and I'll second have to take the derivative of that and multiply by this, because I have two separate functions of x. So I'll do the first one first. That's quite easy. And the second term will look a lot like this, times another factor of minus x over a squared. And I'm going to now invoke again that this is we're looking for a solution at very large x, so only the second term will really matter. So in my Schrödinger's equation, I have a second derivative equals a set of constants times x squared times psi. At least that's what the Schrödinger equation wants. But if I actually look at what the second derivative is, I do indeed have something that's times x squared times the original psi, which is right here. That's equal to psi. So if I just match up constants, I have h bar squared over 2m 1 over a to the 4th equals 1/2 k. Or in other words, a to the 4th is h bar squared over mk. And since I don't like to remember what h bar is, I always like to put c's in there as well. So from looking at very large x, we're already able to place a constraint on what this constant a is. That's in the form of the Schrödinger equation here.